Hey, hello students. Let me try another solution. This one goes back to chapter 23. So chapter 23, and it's from the hard book, the University Physics, chapter 13, volume 2, and it's number 79. I decided to print it here, but it says here that a rectangular circuit containing a resistor R, so I got a little picture here, is pulled at a constant velocity, V, away from a long straight wire carrying a current of I. See below. Derive an expression that gives the current induced in the circuit as a function of the distance x between the near side of the circuit and the wire. All right, well, I'll start with this, is why would there even be a current here? This really goes back to Ohm's law, where the current is the driving force, the voltage, divided by the resistance. And you can see here we have a nice little loop, but we don't seem to have a driving force. We don't seem to have a battery. Now we have a resistor here, but that's where this whole chapter 23 was showing a second way here of making an electric field. That is, we can have a changing magnetic field. And so we need to put a couple things together. The first one here starts with Ohm's law. The second is, and I guess this is the chapter before, oh, by the way, I guess what's Ohm's law? I guess chapter 20. So we got this from chapter 20, but we also have chapter 22, where the magnetic field from a long straight wire follows this equation, and that's, in fact, where we got right-hand rule number 2. And so if you imagine taking your right hand and grabbing this wire, there would be a magnetic field making a loop around it. Maybe if I do the magnetic field in green right here on the left-hand side of the wire, it would be coming out of the screen. So we'll give that with a little dot, and then it would loop around and go in. And the strength of it is given by this equation, which depends upon the current and the distance from the wire. And this is the key then to the problem, because in this chapter, chapter 23, we have that an EMF, or a voltage, if you will, is produced as long as you have a change in some kind of magnetic flux. Let's see, I think your author writes it with this minus N delta flux delta T, the change in flux per time, and calls it Faraday's law. So when you put all of these three things together, you can begin to see that because of the magnetism of chapter 22, there would be a field going in this rectangle. And as you pulled it out, according to this, the field would be getting weaker, so therefore there would be a change, and that's what this says. A change in the flux make a voltage, and then that voltage, according to Ohm's law, going back to chapter 20, would then produce a current. So chapter 20, 22, and 23, we put all those together. In fact, that was my hint for you in the lecture, is if anything's hard about this chapter, well, a lot is hard about this chapter. So there are a lot of things hard about this chapter. And conceptually, this is pretty hard. Fortunately, there's just one major idea for the whole chapter. But what it requires you to do is to put together other things from the previous chapters. And so this is our last chapter, this chapter 23 on electromagnetics. No, I didn't say that well. There is electromagnetic waves. Then we get into optics. Okay, so, but this is a tough concept, and anytime you put ideas from past chapters, like 22 and 20 and 23 all together, it becomes a hard problem. And so you can see that, it is definitely a hard problem here. And let's see then if we can solve that. And so the conceptual picture, hopefully I'm getting across. You pull it out, you change the flux. Flux makes an EMF. and the EMF is a voltage, which creates a current. And so you can put these two together to get your change in flux. So I'm going to put this together, but also what makes it even harder is we're going to have to do some calculus. So let me go to another picture here. I'll kind of draw my own. I'll have a current going up. So here's current I. And I'll just make a rectangle. And if it'll be okay, I won't even bother to put the resistor in there. I will then kind of remind you that it is being pulled with a velocity v. But this equation that says the magnetic field depends on the positioning, R is measured from the wire. And so if the distance of x to the edge of the rectangle, you can see that in this area, and I'll just kind of put a bunch of x's, we would have a magnetic field going into the page here. And as it goes into the page, there is a magnetic field. But as you can see, if the rectangle has a width then of b, and it has a height of a, I'll bring it back into view, see, height of a, width of b, distance x. We would then have to say that the field over on this edge of the rectangle is a little weaker, and so I'll illustrate that with a fewer number of x's. So to figure out the total amount of flux, and so flux, which is the strength of the field times the area, we can't just simply take the field times the area of the rectangle. I mean, you might be tempted to just say, well, the area is A times B. But again, that would only work if the field was uniform over the whole thing. And so what we need to do is to say something like this, that the total flux is a summation of the field times some kind of small area. I'll call it kind of a delta A. And maybe in a different color here, I might take and say if I take a small area, and the smaller the better, so that the field doesn't change, I could say that the flux in that little strip, if you will, is the field at that strip times the area. And then I could take another strip and another strip and another strip and add them all up. And so that's what this little sigma is supposed to be. Or put another way, here's what I'm really saying. I said I'm going to add up an infinite number of strips where I'm going to take the limit as each little strip gets thinner and thinner and thinner. And you're beginning to see how the calculus plays out. This hopefully looks to you like the second fundamental theorem of calculus. This is the definition of an integral. Now, before I kind of take the limit as the area gets smaller, let me change the area of one of these little tiny strips to say, well, it would have a height of A and a width of, and I'll give some kind of symbol here. Let's do kind of maybe a delta x, and so a little tiny piece, delta x. And so that is the area. So really, as the area goes to 0, we're saying delta x goes to 0. And so maybe I can cross that out. And now it even looks more so, I hope, like the integrals you learned in your calculus class. This is then an integration, and I'll use then the elongated s for summation. And so it's an infinite summation of an infinite number of infinitely thin strips. And it would say it's the strength of the magnetic field times x. And then we'll use the calculus symbol, dx, when we actually take the limit. And so again, this right here is a area of a strip. This is the field of it, and then this is adding it up. So in other words, we're going to be adding these up from x equaling x here, and then going out to x plus b. And so again, if we kind of continue here, and so here's my integral, here's from x to x plus b. I'll put in the equation for the magnetic field, mu naught times I over 2 pi. And here I'll kind of make a little adjustment. I mean, we learned it as r, the distance away, but kind of in our discussion, this r has been the x. And so for this particular problem, the r and the x are one and the same. So I'm going to replace the meaning of that r with the symbols I've been using for this problem, which is an x. Then times an a, and then times a dx. And so again, this is going to give me that total flux. And that might actually be the hardest part of the problem. I don't know, it's pretty hard kind of putting all three chapters together. But now it was hard taking then this idea of chapter 23 and applying our calculus to it. Now, fortunately, this calculus is pretty easy. If you remember your integrals, kind of the first thing you want to do is to say, okay, what things do not change, and they can be pulled in front of the integration. We say calculus is a linear operator, and so you can pull it out in front. And so none of these change as we think about adding a strip and another strip and another strip and another strip and another strip. The current doesn't change. It's always the same base current, and all these constants are the same, and the height of each strip doesn't change. And so we're only left with what changes is the position x of where that strip is. And that's what required us to do some calculus. Otherwise, we would have just done kind of the simple algebraic kind of high school level thinking of flux. We would just take area and flux and say they just multiply them together instead of saying it's an infinite sum of an infinite bunch of tiny pieces. And then fortunately, this is an integral that I'm sure you did many times in your calculus class. The answer is just a natural log, and so this would be the natural log of x with the limit from x to x plus b. And maybe I better put page 1 on here. I don't think we'll need more than a second page where we've done the hard stuff. But I'll nonetheless go to page 2 and say, all right, so here is this mu naught IA over 2 pi. And then I'll put in my limits. And so ln of x plus b minus ln of x. Okay, so there's the flux. Okay, now, again, we have the flux, but the next question is, how does it change in time? And so now, again, I'm going to apply a little bit of calculus to this and say, well, if this then is the EMF, and as you pull it across here, I can't imagine it changing uniformly. I mean, the velocity is uniformly, but like when it's close, I have a big concentration here that gets weaker with the flux, and as it gets out, the change between, when the rectangle is way over here, the flux here and the flux here doesn't really change that much because it's only a distance b compared to this whole distance away. And so its change is, well, I guess that was uniformity. I shouldn't even have said that. I should have said just the change here. Here, there'd be a big concentration of flux, and with a huge gradient inside, and over here there'd be a small concentration with a small gradient. But the point is it keeps changing, and every position would be a little bit different. So I probably want something, and again, we're going to have to go back to our calculus, in the limit when time goes to 0 of how the flux changes with time. And so this could be another big challenging part of this problem, because, you know, here I applied my calculus to a summation, so I got an integral. Here I'm applying my calculus to a ratio, which is the derivative. In fact, hopefully you'll recognize that when you take this limit, this is the derivative with respect to time of the flux. And that's how you get this EMF. And so that's what I need to do with this answer here. All right, so now EMF is the derivative with respect to time of this crazy thing. Mu naught IA over 2 pi ln of x plus b minus ln of x. And so now I need to take its derivative. And likewise, the derivative, just like we said earlier, the integral is a linear function. You can pull out the constants. These constants that don't change as the rectangle is being pulled out, I shall just take those out. And then I have the derivative. And it almost sounds like we're just undoing the integral, because when we, had the 1 over x here, and then we took its integral and got ln. If I take the derivative, don't I get back? Except this is the derivative with respect to time, and this was an integral with respect to x. And what I mean by that is I'm going to need the chain rule. So if I take the derivative of this natural log function, I will get 1 over x plus b. But then I will have the derivative with respect to time of the argument, which would be the derivative with respect to x, plus the derivative of b, but b is just the area of the width here of the rectangle, and so that's just a constant, and so the derivative of a constant is 0. And so we end up with that 1 over like we thought, but then this is going to be important here. And then, of course, same thing here. So minus, this would be 1 over x, and then dx dt. And then here's where we might, again, want to kind of read our math a little bit. You can see that each term has a dx dt, and that is then the velocity. That would go back to, wow, physics, the first chapter or second chapter of our 110. And since they each have a v, I'm going to factor it out, and so I get 1 over x plus b plus 1 over x. And that's the EMF. And then one last step. The current then is this EMF divided by the resistance. So now that I got the EMF, mu naught I A V over 2 pi, I will now just divide it by its resistance, and I think I'm done. Let's go back to the question here. Rectangular circuit containing a resistor R is pulled at a constant velocity of V away from a long straight wire carrying a current I. Derive an expression that gives the current induced in the circuit as a function of distance x between the near side and the wire. Yep, and so I am now done. Lots of thinking there. Maybe only 2 pages worth of work, but definitely involving calculus and 3 different chapters. Really a tough problem. I'm tempted to say that this problem would be better if it had a part B, which says now, what about the direction? What direction is this current? Does it go clockwise around this rectangular loop, or counterclockwise. And that's where Lenz's law comes into. And I'm sure the author felt, hey, we've already done a lot. This was a hard problem already. Let's just leave it at that. And I agree. But just for completeness, and anybody still listening who kind of wants to finish up here, let's talk about the direction. So notice that when the wire, rectangular wire, is close to the wire with the constant current, there's going to be a lot of flux. And as we pull it out, there's a little bit of flux. So we're going from a lot going in to just a little bit going in. And Faraday's law says it opposes the change. So we add a lot down to a little, and we want to keep it where it was. And so that means we would want more flux going in. So the current in this loop is going to be set up either clockwise or counterclockwise in such a way that it's going to make more flux going in. And that would result if the current was going up here. So you got to do the right-hand rule number 2, and that would make flux going in. Then it would arc across the top, which would make flux going in. Then it would go down the bottom, and I take my right hand for right-hand rule number 2, and that little piece would make flux going in, and then the same thing here. And so it would be a clockwise. So clockwise if there was a part B asking for what direction. Good problem, tough problem. Hope you were able to get at least some of it. All right, take care.